All right, today we're going to talk about ways that we can recognize linear functions in different forms. Uh, First, let's think about where linear functions belong in the big scheme of things that we've been talking about. We started out talking about relations, and that is the big outer box there. And then inside relations, we had special relations that were called functions. And now inside functions, we have special functions that are called linear functions. And those linear functions have certain characteristics. First, when you look at the graph of a linear function, it's going to graph as a straight line, and it has no breaks, bends, or curves. And we'll take a look at some examples of that in just a few minutes. And then um, linear functions have a constant rate of change, and that's referred to as a slope. Also, when you look at the equation of a linear function, you're going to have no exponent greater than 1. So if you see exponents of 2 and 3 and 4, that would make that not a linear function. You can have no variables in the denominator. That doesn't mean you can't have fractions. You can have fractions, but the variable just will not be in the denominator. And you can have no variables that are multiplied together. And you can have no math operators such as square root or absolute value. All right. So when we look at linear function graphs, we have a few examples here. And if you will look at the ones on the left, those are all graphed as straight lines. And since they both graph as a straight line, then they are linear. When we look at the ones on the right, one of them has all these straight line segments, but they bend and turn and they don't make a straight line. And then the other one is a nice curve. And since the top one has bends and turns and the bottom one is curved, these are nonlinear functions. So looking at a graph, it's pretty easy to tell when you have a linear function and when you don't. All right, when we look at tables, we're going to have to look for the rate of change, and we're looking for that constant rate of change. And so by doing that, we're going to take that first table on the left, and we're going to look at the rate of change between the first line in the table and the second line in the table. The y values increase by 3 and the x values increase by 1. If we look down that table between the second and the third entries, the y value again increases by 3 and the x by 1. And continuing to look at that pattern, we see the y value continues to go up by 3 and the x value by 1. And again, that happens onto the last line in the table. That gives us a rate of change, if you remember that your rate of change is your change in y over your change in x. So when we look at this rate of change, we see positive 3 over positive 1, and it's constant all the way down. So this function is linear because it has a constant rate of change. Let's look at the second table. When we look from the first line to the second line in the table, we see that the y values increase by 2 and the x values increase by 1. Looking on down the table, we see that the y values go up by 4 and the x values go up by 2. That's a little different than the first table that we had. Let's keep looking though. When we go 9 to 15, that value increases by 6, and 2 to 5 increases by 3. And then when we go on to the last line of the table, that goes up by 2, and then the y value goes up by 2, and then the x value goes up by 1. So when you look at this, you may first think, well, this is not going to work. It's not a linear function. However, we have to compare the ratios of those changes. So if we look and we compare the change in y to the change in x for each one of those lines in the table, then we'll see that our first rate of change is 2 over 1. Then we have 4 over 2, 6 over 3, and then we would have had 2 over 1 again. But all of these fractions reduce to 2. 2 over 1 it reduces to 2. 4 over 2 reduces to 2. 6 over 3 reduces to 2. Therefore, the rate of change is constant, and this is a linear function. All right. When we look at the third table, When we look at the third table, we look at the first rate of changes. We see that the y goes down by 3 and the x goes up by 2. And in the next one, the y goes down by 3 and the x is increasing by 2. There again, the y is going down by 3 and the x is increasing by 2. and it continues on to the last line of the table. So when we look at the change in y over the change in x, we're going to see that we have -3 over +2. And it's okay that the rate of change is negative. That would be a -3/2 or a -1.5. But it is constant. And that's the important part for a linear function. It has to be constant. So here the rate of change is constant, so this is linear. Looking at the final table, if we look at the first rate of change, we see y increases by 1 and x increases by 1. When we look at the next change, we see that y increases by 2 and x increases by 1. And then y increases by 4 and x increases by 1. And then y increases by, then y increases by 8 and x increases by 1. So if we're going to look at the change in y over the change in x, then we have 1 over 1 for our first rate of change. Then we have 2 over 1, 4 over 1, and 8 over 1. And none of those fractions reduce to the same thing. Therefore, the rate of change is not constant, and this is a nonlinear function. All right, let's look at equations. When we look at equations, we need to be considering that list of criteria that we have before. So when we look at the y equals 3x minus 4, we're going to look at the variables. The x and the y are not multiplied together. They have no exponents greater than 1. And we don't have any square roots or absolute values or any other math operators other than add, subtract, multiply, and divide. So this is linear for the reasons we just stated. If we look at x squared minus y equals 4, we're going to notice that we have an exponent of 2. That immediately tells us that this is nonlinear because it has an exponent of 2. Looking at the -3/5 x plus 4y equals -3, you might want to say, well, that has fractions in it, so it's, we need to think about that. But look at the fraction. The variable is not in the denominator. X is just multiplied by that fraction, and there are no exponents greater than 1, and therefore this is linear. When we look at y equals the absolute value of x, that's x inside those straight little bars there, we know that this is nonlinear because of the absolute value. When we look at the third one on the left, we have 2/3 x minus 4/3 y equals 3/4. Again, lots of fractions, but the variables are not in the denominator. Therefore, this is linear. And when we look at y equals the square root of x minus 7, we know immediately that that is nonlinear because of the square root symbol. Then the last one on the left-hand side, we have x plus 2 divided by 3 equals 5y divided by 2. Again, we have some crazy-looking fractions, but the x and the y are both in the numerator. No variables are in the denominator. No variables are multiplied together. And so we have a linear function there. And then the last one on the right-hand side, we have 1 over x plus 2 equals 5y. This one has a fraction, and if you'll notice, the x is in the denominator for 1 over x right there. Therefore, this is nonlinear because we have a variable in the denominator. All right. So, again, just to review, when we look at linear functions, we're looking for graphs that have straight lines with no bends, breaks, or curves. We're looking for tables and equations and graphs that have a constant rate of change. We're looking at equations. We've got to think about exponents that are not greater than 1. We have no variables in the denominator, no variables multiplied, no square roots or absolute values. All right, you're going to have some practice with this, and hopefully